Hello, everyone. On this unit of industrial chemistry, we're going to be talking about a lot of the factors that go into designing a chemical reactor. So, in order to start this off, we need to do a quick review of equilibrium. So, a lot of this should look familiar, but towards the end, we're going to see some terms and tricks that are a little bit more unique to chemical engineering, but still fairly widely applicable. So, first thing we need to think about is when we're dealing with reactors, that means we're dealing with chemical reactions. So these are our good old friend, the unit process. So what we're going to be focusing in on today is a little bit more of reaction engineering. So more or less, how do you try and optimize this reaction? And while it and there turns out to be two major features when we're trying to optimize reactions. And most of you should be familiar with these two concepts. The first is going to be thermodynamic considerations. So this is more a factor of what can happen and what will or should happen. However, just because a reaction is favored doesn't mean it's going to happen quickly. So since time is money, we also need to have a good study of kinetics. And today we're going to be focusing in on mostly the thermodynamic considerations, and next time we'll focus a little bit more on the kinetics. So we're going to be looking at these equilibrium processes, and if I let my system go for an infinite amount of time, what would my reaction solution end up looking like? So biggest thing is, what are going to be some good ways to describe an equilibrium process? So one of our good old standards is our old friend, the equilibrium constant. So this is going to be the ratio of the product distribution, again, at an equilibrium or infinite time consideration. However, we can also describe this in an energy sense using our good old friend, the Gibbs free energy, and in the amount of heat it requires to is released or consumed by a reaction, and with our good old metric enthalpy, which we've used quite extensively throughout this course. So, worth noting, all of these are going to be intrinsic chemical properties we can look at. But one of the things that's worth noting is a lot of the chemical definitions we've been using in our previous courses, such as analytical and physical chemistry, they really do start breaking down at high temperature and high pressure, most specifically at high pressures and concentrations. Unfortunately, to drive large-scale productions of products, it's usually these high pressures and concentration conditions that are going to dominate industrial chemistry. So in chemistry, we're typically going to write these out as, again, a ratio of pressures or concentrations, whether we're looking at K, Kc. And this gives us an idea of what our reactor outputs are going to look like if they behave under ideal or infinite time considerations. But again, this is going to assume ideal behavior. So in reality, don't forget, we're going to need to make use of activities and activity coefficients. But again, a lot of industrial reactions like performing reactions in the gas phase, where we have increased reaction rates. So we're going to also want to make use of things like fugacities and the fugacity coefficients. So again, one of the big things we're going to want to think about is how and when are our systems going to deviate from ideal behavior. So biggest thing is we're going to see the biggest deviations from ideal behavior, especially in gas conditions at high pressures, where they behave a little bit more like a liquid and a little bit less like a gas. So in analytical chemistry, and physical chemistry, we gave you a large series of equations we could use to try and approximate what our fugacity coefficients would be. However, in a real industrial chemistry setting, the classic answer is almost always the same. Turns out there's a table for it. So being able to hunt down a lot of our a lot of our industrial chemistry resources to look for these tables of conditions and coefficients can be hugely advantageous. So again, we can take a look at what happens to the fugacity coefficients as I increase temperature, at which you're going to notice the fugacity coefficients start becoming a little closer to 1, which means more ideal behavior, as well as what happens when I increase the pressure, at which point everything kind of goes haywire. And the fugacity ends up being almost a quarter of what the predicted ideal gas pressure, uh, uh, what the concentration would be predicted from the ideal gas law alone. So one of the real other considerations we need to be taking into account for is that these activity coefficients are also going to highly impact are really going to be highly impacted by the favorability or energy of the systems. So again, we can also look at what the activity of a species is by looking at how much the chemical potential deviates from the chemical potential of the under ideal conditions, where again, just as a reminder, chemical potential is pretty much the same thing as the molar free energy for an individual species. So again, one of the other considerations to make note of is in an industrial chemical setting, we're often going to be looking up these non-ideal chemical potentials through the use of a lot of tables and external resources. So if I'm dealing with a non-ideal system, we often need to make note of the fact that we should be including our fugacity or activity coefficients when trying to evaluate the K for a reaction. And again, if there's stoichiometric coefficients, don't forget about including those as well. So again, here ends up being the real trick of, if I have a good set of tables that will give me the fugacity coefficients for a given pressure of the system, how will I end up using those to end up solving for the equilibrium constant? So here's the real trick. So I can go ahead and using the ideal pressure, I can go ahead and try and solve for my fugacity coefficients. But the issue is, as soon as I have my fugacity coefficients, the pressure in my system may end up changing, which means in a real sense, we often have to solve these sort of problems in a more iterative approach. So then using our new fugacity coefficients, we'll solve for our new pressures, which we'll then use to recalculate our new total pressures, look up our new fugacity coefficients. And as you can imagine, it can take a while for a lot of our pressure values to converge, especially when we're dealing with systems that deviate from more of this kind of ideal gas stripping approach, where I may end up having a change in the number of products versus reactants, so my total pressure can really end up changing significantly along the way. So here's going to be the real question: is there going to be a better way? Well, a lot of the improved ways end up becoming about using computer programs to try and automatically solve these equations. However, all of these assume we already know our equilibrium constant. So let's say I have a new reaction and I need to try and determine my equilibrium constant. In these cases, we're typically going to try to use our Gibbs free energy. And again, tend to hope that we're in an ideal solution. But again, watch out, because a lot of times we are not working at room temperature. So a lot of our standard state Gibbs free energies need to end up being modified. So the classic approach to this is trying to modify our Gibbs free energies of reactions using our classic Gibbs equation, where the major modification of the Gibbs free energy with temperature is going to be based on the entropy of reaction. And the entropy tends to be relatively constant with temperature. However, as we've seen in physical chemistry, the enthalpy can actually have quite a large dependence upon temperature, especially if I'm uh, working more than, say, 25 or 50 degrees away from my reference temperature. So let's say I need to try and determine my enthalpy and thus my free energy at uh, these extreme temperature conditions. So in a simple case, the simplest approach is going to simply be trying to figure out what the enthalpy of our products and reactants are at these new conditions, and then using that to modify how much our enthalpy of reaction changes under these new sets. So ideally, we should be able to find our enthalpy of products or reactants at our new temperature using our good old friend, the Kirchhoff's law, where it's just going to simply be related to the heat capacity times the change in temperature. However, remember, our heat capacity itself is going to be temperature dependent. So if I'm dealing with a temperature change more than about 100 Kelvin, which is fairly common in industrial chemistry, I'm going to need a new solution. And for that, we're going to be using our good old friend, which we brought up earlier in the course, a linear expanded form of our heat capacities. And there's, again, watch out, many different forms of these, which you can then modify by taking the integral of our heat capacity with temperature to get our new enthalpy change over how much our enthalpy will change over this temperature region. So again, this whole process can be quite tedious, especially under fairly large temperature differences, where we may need to repeat this process with entropy as well as enthalpy. So again, a lot of the better ways to try and find how our free energy uh, of reaction changes with the species ends up becoming the making use of computer models. But it turns out there's also a great deal of other resources out there. And they often end up uh, coming from the good old chemical industry standby large tables of pre-solved data. As a nice alternative for the more modern approach, which is essentially computer calculated values. However, there's also another old style approach which can be really useful when looking at specific types of chemical reactions, and that's essentially using an Ellingham diagram. So the idea of an Ellingham diagram is looking at how the free energies of reaction change as a function of temperature. So the classic Ellingham diagram is looking at oxidation reactions of fairly common metal species, as well as carbon-based species like CO, carbon monoxide, and strict carbons such as found in coke or coal. So in these cases, we tend to assume that the pressure of O2 is at a standard state 1 molar or 1 atm concentration. And then we essentially look at what happens to the favorability of any given reaction as I increase the temperature. And we can use these to help determine a lot about when a reaction will occur. So for example, the lower down we get in the table, the more favorable the reaction is and likely it is to occur. So let's take a look down here at the bottom of the table. If I go ahead and mix magnesium and aluminum where I have an oxygen source, magnesium will be the preferential oxidation reaction that will take place over any formation of an aluminum ore. Simultaneously, you can also use this to kind of pair reactions involved. So if I mixed magnesium and aluminum oxide, magnesium is going to steal all of the oxygen from the aluminum oxide because it is a much more favorable reaction. So typically what you can imagine is if I pair any two of these lines, the bottom reaction, the bottom reaction will steal the oxygen from any other product species. And this can be quite advantageous because it turns out if I mix magnesium metal with aluminum oxide, zinc oxide, carbon dioxide, carbon monoxide, uh, iron oxides, or cupric oxides, I am always going to end up with the same product, magnesium oxide. It will steal oxygen from anything. So what we can do is, using these Ellingham diagrams, we can help determine the equilibrium constant for any relevant reaction. Because what we can do is, uh, by identifying our reactions of choice and our temperatures, we can look up our free energies of reaction. And then by pairing two sets of free energies uh, of reaction, I can generate an overall free energy of activation and thus an equilibrium constant. Uh, and we can then use these equilibrium constants to determine the pressures of the gases that may be ending up released or consumed in these reactions. So in the typical Ellingham diagram, what you can then do is by pairing up all the reactions, you may be able to find the concentration of any free oxygen present in the system. However, one of the things that is worth noting is that these free energies will be dependent upon the pressure of other gases such as O2, CO or CO2 ratios, and hydrogen and water ratios. So what you can essentially do is, let's say I know that I've got a relatively uh, low O2 pressure where I may have 10 to the negative 16th O2. I can essentially follow this line along and figure out where my free energy ends up being by where it intersects the relevant line. So again, this can be a fairly efficient way to determine the free energies of various reaction species. However, it can be a little bit trickier making use of the Ellingham diagrams to tell you what these relevant gas pressures are. And you may end up being lucky and being able to find a resource, such as I provided you on the website, which lets you automatically recalculate the Ellingham diagram for various gas concentrations. So let's go ahead and look at some quick example problems. So let's take a look uh, at zinc oxide and zirconium oxide, and we may see some interesting behaviors. So this is kind of a more reduced notation for an Ellingham diagram, simply due to the fact that there is a lot of species present. So when I say zinc oxide, what I'm talking about is the formation of zinc plus a half equivalent of oxygen to form zinc oxide. And we tend to see a relatively straight increase with a relatively straight decrease in the favorability of this reaction as I go to higher temperature. So first thing I should be trying to figure out is, why is this reaction less favorable as I go to higher temperatures? And it turns out that it's all about phases, because I start with a solid and a gas producing a solid. Well, that turns out to be entropically disfavored. And so as I go to higher temperatures, I'm going to be favoring this product less and less because entropy says so. And that actually ends up providing some insight of why I see a change in the behavior at this point. Because now I suddenly go from this reaction becoming less disfavored at a constant rate, which is entirely, and you'll find that at this point, the slope will be due almost entirely to the entropy of reaction. And at this point, it quickly becomes much less favored. And the reason why is at this point, I don't go from solid zinc and gaseous oxygen forming solid zinc oxide. I go from liquid zinc to plus gaseous oxygen forming zinc oxide. And this makes the reaction much more disfavored disfavored than for solid zinc. So it turns out just by using the Ellingham diagram, I can determine the melting point of of solid zinc, which again is fairly useful. Now, if I go to zirconium oxide, I see a little bit more interesting behavior because I start here where I have solid zirconium, and then at about 300 degrees, I end up seeing the melting point of zirconium oxide. So it becomes a little bit more, I see a phase change of zirconium, which ends up taking on a more disfavored form, which speeds up how temperature affects the favorability of this reaction. Then at a very interesting point around 1200 degrees C, we see a very odd case where the reaction now becomes more favorable as I go to higher temp. And the reason why is actually fairly straightforward, because I now go from zirconium oxide plus oxygen, making solid zirconium oxide, to liquid zirconium oxide. And making that liquid zirconium oxide becomes favorable. And so for this short region, zirconium oxide is temperature favored, or is entropically favored. However, we quickly reach the point at which the zirconium solid I have zirconium solid as my reactant, to where I have zirconium liquid as my reactant, and the reaction again becomes entropically disfavored. Similarly, I can also use some of this information about how I would try and go about forming solid manganese or nickel. So let's start by taking the case of nickel. So nickel is often going to be found in the form of nickel oxide as a mineral. And so as I go to higher temperatures, this reaction becomes less and less favored. And so I'm more likely to be able to drive a nickel oxide to a solid nickel product. So this tells me a good first piece of information, which is high temperatures will tend to favor the formation of solid nickel. However, the real problem is that at any of the conditions that any temperatures I can realistically drive this reaction to, the release of oxygen from my nickel oxide is still going to be generally disfavored, as it's well below zero. However, if I'm able to find a place that the oxygen might preferentially want to go, I might have some luck. And it turns out that's where the real trick of a lot of metallurgy lies, because I just need to find another substance which is lower than this line. And there's a lot of choices. You can imagine mixing up nickel oxide with solid tin, and that would work. But it turns out there is a good oxygen acceptor out there, and it's sitting right here. CO2. This line is going to be the formation of CO2 from solid carbon. So as long as I mix in a little bit of coal or coke with nickel oxide, and I raise the temperature above about 400 degrees, I should be able to get oxygen transfer from the nickel oxide to the coke and form my nice solid nickel. It turns out this is exactly one of the go-to ways of producing pure nickel metal, and brings you to early metallurgy. Manganese can be a little bit trickier because manganese oxide is a much more disfavored species, as it is much lower down in the Ellingham diagram. So trying to find a good oxygen acceptor for manganese can be a little bit trickier. Things like pure silicon or titanium might work, but I'd also need to find a way to get those pure species. And that's where another important line ends up happening. Because it turns out that coke or coal can save my butt again, because it turns out at high temperatures, coal will, instead of wanting to form CO2, will form CO as long as I'm under low oxygen conditions. So if I get to a high enough temperature, say about 12 or 1300 degrees, I can reach this critical point at which I mixing manganese oxide with coal will preferentially produce carbon monoxide and pure manganese metal. So essentially any point after this crossover. So this gives us a good way of forming manganese metal through simple application of heat and the correct starting materials. It also, one of the things I really love about an Ellingham diagram is it also tells me a lot about what's going to be an easier metal to form and the relative temperature regimes where you can form them. So let's look at early metallurgy. So two of the classic elements that defined early civilization is copper, from which we can make bronze, and iron. So it turns out copper is relatively easy to make. As long as I get high enough temperatures to overcome the kinetic behavior, cupric oxide will always preferentially form solid copper whenever it's exposed to any good pure metal species or coal. So this is actually a really easy metal to purify, thus the early Bronze Age, especially when you're able to eventually purify nickel or tin as alloying agents. However, iron becomes much trickier because for iron, if I'm forming, say, something like an iron mono iron oxide or ferric iron oxide, which ends up being a little bit further down here, I have to start getting to temperatures a little bit over 500 degrees C. And it's much harder to form to get a forge up to those sorts of temperatures, and much more important that I have a ready source of carbon or coal present in large concentrations. So this is one of the reasons we get to early iron and steel making. And so what you can do is essentially watch the progression of society through an Ellingham diagram. The first species that are easy to isolate on their own are going to be things like silver or mercury, which can readily undergo oxygen loss. And then we can eventually purify things like copper and lead, which are also very important species in early development. And then I can start making bronze once I can alloy copper with lead, nickel, or tin. However, it becomes much harder to hit things like iron, characterizing the Iron Age in classical civilization. However, much more exotic elements such as zinc, manganese, silicon, and titanium, which tend to categorize modern civilization, are going to be much more late in the metallurgically purification process. However, in order to reach elements down here, you need to go beyond methods that you can get from simple application of heat and carbon. So in order to purify things like uranium, aluminum, zirconium, beryllium, or calcium, you need to go to electrochemical methods, which have essentially characterized the last century. So one of the things I really want you to kind of take home about how an industrial chemist makes use of a lot of these thermodynamical principles is how you can tend to make use of graphs, tables, and diagrams to get a lot of the same information that we have to often determine in much harder, more rigorous approaches in classic chemistry. So next time, we're going to start addressing some topics of kinetics and how they really interface with industrial scale reactions. Till then, take care.